So we are team chunkers. So we were trying to do different kinds of chunking and actually address those big loss spikes when that you saw in the previous plots. I mean, I guess the motivation already been given. It's we want to fine tune models on reasoning traces. So you have the CR1, it generates tens of thousands of tokens. And if you want to teach smaller models to also be good at it, we have to fine tune on this data. So that's, I think, part of the reasons why these techniques are still not very well explored, because people never needed to fine tune such long context before. So that's why the default settings, default libraries, they don't do so well now. I think soon enough they'll build better, but now there is some interesting questions. Okay, so we tried. So what we tried is different kind of chunking. So even in the past, we already found through some GPU profiling that if you chunk your completions, so let's say instead of training on 16K, you still train on 16K, but you take 2,000, compute the loss in 2,000, you save it, you go on to the next 2,000, compute the loss added to the previous one, and sort of keep iterating this way. So this already gives a pretty good savings. So let me first go through them. So again, we're using the similar profiler. So this is just the baseline. So it shoots up to 60 gig of memory. So the speed is about 3 seconds per iteration. So after we added the chunking I just described, so we can get it down to 43. You can ignore the circle. 43, so that's pretty good saving. And the time is exactly the same. So next, so something interesting that we noticed. So we actually tried to build like a way to understand the GPU memory better, and we tried to improve the profiler, but get like into really the details. So what helped is just literally printing torch good allocated memory. Put the print statement wherever you like, how much memory is there. And so this showed something interesting. So let's say here we print this, like the before, then after computing the logits and after computing the loss. Okay, so this looks good. It's much better than the vanilla implementation. But as you can see, so as it goes through the chunks, the memory increases quite a lot. And that seemed a little bit weird. Like, why should the memory increase as it crosses the chunk? Like, in the ideal world, we should compute the gradient, and we can have it stored by some loss. So it seems like unnatural that it increases. And so that led to a next idea. So what if we do something similar to what gradient accumulation does? So gradient accumulation goes over batches, and it says, I'm going to compute a gradient on batch number 1. Then I'm not going to update my parameters. I'm just going to compute a gradient on batch number 2. And after that, I can do it as many times as I want, and then I will update my parameters. So this allows you to have larger batch sizes while still, being limited in memory. So why don't we do the same for the sequences? So as I go over my chunks, so previously I was summing up the losses. And somehow, for some reason, my memory was increasing. So we said, let's just do a backward after every chunk. So we thought this might help. And indeed it did. So this is after we did this, what we call accumulation chunking. So you can see we do not have any loss spikes. Like the memory doesn't spike when computing the loss at all. It's basically just gone. So we have a very clean so memory allocation here. So we are down to 23 gigabytes, which is pretty good. I would say, so one drawback I should notice, I think maybe with a bit more skill and implementation, this can be fixed, but now it takes long. So it was before 3 seconds. Now it's up to 18 seconds. I think there is it's just not, done very optimally. It's a hackathon, so I have to rush a bit, but I think it's pretty cool. Like even with the speed up, like it's still valuable, even if that's unavoidable. Sorry, not speed up. Extra time, because sometimes memory is really what we are bounded by. Right now, I think you could maybe train on like 100K fish before just so yeah, so these are the main findings. So I also did a quick correction check. So this is just to make sure the gradients are identical. So running 10 iterations over the same data set. So we checked the cation similarity of like arbitrary transformer layers 15 MLP gated approach, just a random one in the middle. And so we double check that the gradient are the same, just to make sure the gradient is enough. So we have vanilla, we have chunky, and we have GP chunk is what is accumulation chunk last years. So you can see that the gradients are all the same after numerical differences. So yeah, this is the time distance. 0 is the same, 1 is orthogonal. So that's all. Yeah, so any questions so far? We have one last thing also.
Sorry, just accumulation chunking, you're just updating the weights as you go along the way in chunks. Is that
You don't update the weights. You compute the gradients and then you just keep it. You don't touch your weights. Then you move on to the next chunk, you compute the gradient again, you add it to the previous one. And you keep moving along this.
okay?
So this basically avoids this sort of weird grooves in the GPU memory as we go through the chunks. Maybe there are other ways to get rid of it, but that's kind of the one thing we tried. All right, so and then Felipe, you want to talk over the other thing? There.
Yes, I can talk about. Can you hear me?
Yeah.
Okay, so the final idea was an idea inspired by a function that we found on Unsloth package. So instead of like chunking sequences of text, what they do is that they chunk the vocabulary. So the idea behind like why this should work is that, like for example, we are working with Quen, and the vocabulary is like massive. It has more than 150,000 tokens. So like at the last layer, we would expect to have like a very big tensor, like with one of the dimensions being like the size of the vocabulary. So we want to avoid the computation of this big tensor so we can save a lot of memory. So what we do here is like we have this 150,000 tokens and we chunk them in like groups of 10,000. And we perform computations in this group separately, and then we aggregate everything together. And our results show that so basically we are comparing against the second idea, which is chunking with sequences. So this plot, as you can see, is the one chunking with sequences, and we use around 44 gigabytes. But if you go down a bit, we can see the other idea that reduces to less than 20 gigabytes. And then at the end, we have a table showing the losses are close to each other, and then both are going down. Yeah.
Yeah,
So
I think
that
in this case of the something changed a bit, but it's much faster. Did you compute the time for the iteration?
I have yeah.
Okay.
I don't think but I think that the time was very close. Like both, they didn't differ a lot. Yeah.
Okay, so I think now if you put it together, maybe you don't need GPUs anymore. By the way, fun thing, a request to maybe the Sunday Club is, we were really writing this. So as you can see, the blog post consists of print screens. Like even for something like that, it was just quicker to just grab a print screen and shove it in here. Like trying to get a markdown table. So maybe that's the idea for an ad.
To what, parse the code from there? Or?
Well, now take this because it looks kind of unprofessional and maybe turn it into like a markdown table or something. Like, I mean, pictures are pictures, they're fine, I suppose. But like this is also a print screen of a text.
Yeah.
I mean, I think the probably like visual language models can get the numbers out and then like put it in markdown.
You can also probably make a button, so just like you press it and prepares a draft of a post about this insights on the
like
media.
make it look normal, like
yeah,
kind of like
to like make it look professional.
Yeah, that'd be pretty cool. Okay.
Do you guys think it's like, because it's kind of surprising that if you can get such a memory optimization increase, like it basically feels like it should be a standard part of like Transformers library.
Like, I think, well, I mean, Transformers had many issues.
Yeah.
I think the reason it's so far like not so suboptimal is just because fine tuning on the super long, like even before we had RAP, but you don't fine tune on long completions. You have long context, and so in that case, these problems do not come up. like you will not have the memory spike due to loss computation. So I think it's just people never had this problem. So
So like, doesn't make much sense to make a PR to transformers.
no, I think for now it does. Like, I mean, but this code does not, it's a pure PyTorch, right? So if you wanted to work with transformers, we would need to like actually put it in the transformers to make the PR.
But when is it on transformers or where did you get
No, the code is just pure PyTorch reimplementations it did before actually.
Oh, so you just like,
Plan architecture coded in PyTorch. With like, we were sort of just learning steps. That's I think the start code. But I tested with transformers, so you can also do GPU memory profiling with transformers. So I could sort of like use the same memory. Like the basic version, what I call vanilla, is
to also know that like there are like I mentioned on Slot sort of specializing in that long context fine tuning regime where they have like that's where you guys said you found the other optimizations for. So I think yeah them and then also Torch Tune also. And the Transformers library, like you don't use to train models if you're serious at all. It's on Slot, for instance, like they do a lot of like key patching basically of the Transformers library and models in there. Just because like there's so many models to support in each one, you have to go and like make sure that's not reasonable for you to go and update that entirely. So they just sort of like branch off of it instead. With trainers off of it.
I mean, this could be something fun to like tag on Sloss guys in the Twitter post and see if they like does they already done it or maybe they want to do something like that. Probably better.
wait, what's Unsolved model? Do they have like a GitHub can contribute to or?
Yeah, and Sloss is the like essentially like a GitHub where started with like two brothers also doing this type of hackathon style thing. Pretty much still them. So they essentially go through the code of like open repos or like implementations of LLMs and find bugs and issues. They also like they can write their own Trident kernels, and that's something also we can explore at some point. So I mean, a lot of things they've done was like very good for LoRa fine tuning because there you multiply 12 matrices, and the default behavior of like autograd is like it doesn't do it well. You know, it doesn't sort of transpose things well. So that's one thing they did, but they also did a bunch of other stuff.
Right, that's all.